Hi everyone, I'm Tony Neer from the University of Minnesota. In this work, we study how cybersickness carryover effects affect statistical power of within-subject experiments. Researchers need to conduct comparative cybersickness experiment with multiple conditions when evaluating new cybersickness mitigation technique. They can use a within-subject design or a between-subject design. Between subjects design allows more flexibility but requires more participants. Within subjects design are used more often because it requires less participants and provides a higher statistical power. However, for cybersickness research, carryover effect is a critical issue for within subject design because the symptoms takes a long time to wash out. Counterbalancing can average out the impact of carryover effects across conditions. However, this will increase the dispersion of the data and reduce the experiment's power. Some researchers used over 24 hours washout period to avoid carryover effects. Other researchers use shorter washout periods so that they can finish all conditions in a single lab visit. However, the impact of carryover effects on this is not systematically studied. In this work, we would like to quantify carryover effects impact on the within-subject study's power. To do that, we conducted a meta-analysis and a simulated power analysis. Let's assume we are conducting a study with two conditions. We ensure homogeneity in all variables except for the stimulus between conditions. Because of carryover effect, we'll have a counterbalance experiment design like this. For one of the conditions, say condition 1, we have n data points, which are SSQ scores in this case. By definition, the overall standard deviation is this equation. However, the second session is affected by carryover effects. The mean of the second session is increased by ME. We need to know ME to quantify the carryover effects in within subjects design. In this case, the combined standard deviation SDC is described by the new equation, and SDC is the result reported in papers, which is greater than SD without carryover effects. Using our previous equation, we can represent ME in this way. Reminder, our goal is to estimate ME here. However, only the combined standard deviation SDC is reported in papers. So instead, we use the mean and Cohen's d effect size of delta SSQ scores to replace the SD. The result is a quadratic equation of ME. We can represent the carryover effect ME by solving this equation. Parameters C1 and C2 are representing the Cohen's d of studies with and without carryover effects. Now, we need the effect size for studies with different designs. We conducted a meta-analysis to collect data from previous papers. I'll skip the details due to time constraints. We collected 136 data points from 45 papers. Each data point is a mean and standard deviation pair reported for a condition. We categorize experiments into three conditions. First are between subject studies. Within subject studies are broken into two categories. Long washout periods refer to those with over 24 hours washout periods, and short washout periods are those of 10 to 15 minutes. We conducted a meta-regression to estimate the effect sizes of those three designs. We found a significant difference between designs, and the estimated effect sizes were listed here. Before we use effect sizes from previous studies on the solution of ME, we should remember that the solution was for experiments with two conditions. And the data we collected includes studies with three or more conditions. The dispersion of data will further increase as more conditions are involved. We notice that studies with three conditions have twice the impact of carryover effects on standard deviation than studies with two conditions. As a result, we adjusted our estimations accordingly. Using the adjusted effect sizes, we can plug them into the representation of ME. Here are the results for within subjects long design and within subjects short design. And finally, the results from between subjects design. For studies with long washout periods, we found the carryover effect is minus 25% of the symptoms in the first session. For studies with short washout period, we found the carryover effect to be 63% of the first session symptoms. And we can cross-check our results with previous findings. In an experiment studying cybersickness adaptation, Doty et al. Found that participants' average SSQ scores reduced 25.5% from day 1 to day 2, which is very close to our estimation. We also found that after a short washout period, 63% of symptoms from previous studies are kept, and carryover effects reported by previous papers were also around 60 to 70%. In summary, the carryover effects we estimated are in agreement with other previous studies. Now, using the estimated carryover effects ME, we can use simulation to evaluate the impact of long and short washout periods on statistical power. By definition, power is the probability of detecting a significant effect using a given test in a given experiment context. In our simulation, we use the following parameters. We have two conditions: an experimental condition with an average SSQ score of 30 and a control condition with an average SSQ score of 50. Each condition has 30 participants, and we randomly generate data for 10,000 times. Finally, we conducted statistical tests and count the number of significant results. The results showed that between subjects design had a power of 0.76. And without any carryover effects, within subjects have a power of 99. And using long washout periods can give you the same power. However, if you are using short washout period, carryover effects can drop your power to 0.59. Our results showed that a 10 to 15 minute break is impossible to wash out all symptoms. Around 69% of symptoms will still persist after the break. Using a short washout period can significantly reduce the power of your study. That being said, it is easier to do cybersickness studies with short washout period. However, you'll reduce your chance of making a scientific discovery when you use it. Thank you for listening.